So for our next topic, we have a couple of special limits involving sine and cosine. As we saw, of course, the sine, all the trig functions like sine and cosine can be evaluated by substitution wherever they're defined. But there are a couple of limits of the form sine theta over theta and 1 minus cosine theta over theta, where as theta approaches zero, where it's worth knowing that these limits are equal to 1 and 0 respectively, as I've written here and here. So the idea, of course, is that, as we had talked about before, when substitution gives you 0 over 0, that doesn't mean the limit doesn't exist. It just means you have to do some more work to evaluate it. We will learn later on in the course a specific technique that can be used to evaluate these limits, but at this point in the course, it's just worth knowing, and this does come up in problems, that this limit here, limit is theta approaches 0 of sine theta over theta equals 1. Of course, sine of 0 is 0, and when theta is 0, then that's 0. So this is a 0 over 0 limit, and since cosine of 0 is 1, 1 minus cosine over theta as theta approaches 0 is also a 0 over 0 limit, and that one happens to equal 0. So the more general point of this is it appears, we'll write it, we will show it here, is that assuming that u is some function of x that is some function of x that is approaching 0, as long as u approaches 0 and x approaches 0, then the limit of sine u over u also equals 1. That's kind of a mouthful, so I just wanted to show you what I actually meant by that. Here, for example, that's not what I meant to write. Here, we have the limit as x approaches 0 of sine 3x over 3x, and that does in fact equal 1. So as long as, let's put these in green, as long as this actually matches this, and these two expressions are actually approaching 0 when x approaches 0, then this limit will also be 1. So I've put up on the right side, I've put up another example of that, sine of square root of x over square root of x as x approaches 0 from the positive side. That equals 1. And of course I have to put in that this is the positive side because I can't put numbers less than 0 under the square root sign, so that's why I had to write it that way. Okay, so let's do a couple of examples with this. So let's evaluate the limit as x approaches 0 of sine 3x over sine 5x. Let me just write up here the fact that we know that the limit as theta approaches 0 of sine theta over theta is equal to 1. So these whatever is in this position and this position, they have to match each other in order for this to work. So that's what we have to get this to do. It's also, I just want to point one thing out before we start this. The limit as theta approaches 0 of theta over sine theta is equal to the limit as theta approaches 0 of 1 over sine theta over theta. So I'm just playing around with reciprocals here when I do this. And then by the limit laws, that is equal to the limit as theta approaches, sorry, let me just put this up here. That's equal to the limit as theta approaches 0 of the constant 1 over the limit as theta approaches 0 of sine theta over theta. So that, by substitution, equals 1 over 1, or 1. So the point is, the same rule that tells us that the limit of sine theta over theta is 1 also tells us that the limit of theta over... that's not how I want to write that. Tells us the limit of theta over sine theta is also equal to 1. So we can use both of those, and that'll simplify this calculation quite a bit. So okay, so let's go back to this. We have sine of 3x over sine 5x. As x is approaching 0, we can see that substitution would give us 0 over 0. So we're going to have to use one of these rules. Let me show you how to do that. This is equal to the limit as x approaches 0 of sine 3x over sine of 5x times 3x over 3x times 5x over 5x. Now, why did I do that? Well, basically because I can. I mean, it's certainly the case that all I'm doing here is multiplying the expression by 1. 3x over 3x is 1, and so is 5x over 5x, but that's going to help me get into the form that I need. So let's rewrite this a little bit. Let's rearrange. I'm just going to put brackets around this so it's clear we're taking that whole limit. I just want to rearrange these terms a bit. So notice that these terms kind of pair with each other, the sine 3x and 3x. So that's going to be sine 3x over 3x. Now, what do I have to do? I have to, actually, let's do one of the other terms. This term is going to pair with this term. So now I can write in 5x over sine of 5x. And the only things that I have left to deal with are this one and this one. These are the only two terms that haven't been used up yet. So this is going to come out to, this is going to be 3x over, over 5x. So there were 6 terms, 3 on the bottom and 3 on top, and I've now used them all up. All I've done is rearrange their order. But look what happens here when I do this. I have the limit as x approaches 0 of sine 3x over 3x times the limit as x approaches 0 of 5x over sine 5x times the limit as x approaches 0 of 3x over 5x. Well, I can evaluate all of these because I know that this first term is just equal to 1. That's using that rule there up in the corner. And the second term is also equal to 1. That's now using this rule that we sort of just created over here, that I can flip the fraction around and I get the same result. And this limit here, limit as x approaches 0 of 3x over 5x, we learned in the last lecture that you can simply cancel those terms because even though we can't divide by 0, the one point we don't care about when evaluating a limit is the actual approach point, so that's going to equal 3/5. So this is equal to 3 over 5. I want to do another example that's maybe a little bit more complicated, but it just demonstrates how some of these trig functions interact with each other. So we have here is evaluate the limit as x approaches 0 of sine squared 3x over tan squared 4x. Now what we know is that sine of 0 is 0 and tan of 0 is 0. So this is in fact a 0 over 0 limit, and we're going to have to use what we know about the sine and cosine functions in order to be able to evaluate it. I'll just put up here again, we know that the limit as theta approaches 0 of sine theta over theta is equal to 1. So we're going to try to use that fact here. So let's rewrite this a little bit. The key to understanding how to use tan in these limits is to realize that tangent is sine over cosine, and usually when you unpack it that way, some strategies will appear. So this is going to equal the limit as x approaches 0 of sine squared 3x over tangent squared 4x. I'm going to rewrite as sine squared 4x over cosine squared 4x. And by rearrangement, that's going to be the limit as x approaches 0 of sine squared 3x over sine squared 4x times cosine squared 4x. So it's just going to be that entire limit. Now, the interesting thing is I can get rid of that cosine squared right away, and this is one of the keys to remember. Cosine of 0 is not 0, which means that we don't usually have a problem with that. What we can do is, since cosine of 0 is 1, I can simply rewrite this as the limit as x approaches 0 of sine squared 3x over sine squared 4x times the limit as x approaches 0 of cosine squared 4x, where this expression here is just equal to 1. So this is going to equal just the limit as x approaches 0 of sine squared 3x over sine squared 4x. So now I can deal with how to evaluate that using the other techniques that we used. Recall, of course, that sine squared of anything, of u, is just equal to sine of u times sine of u. So what I have on top are 2 factors of sine 3x, and on the bottom I have 2 factors of sine 4x. So let's rewrite this as, let's just multiply here by 3x over 3x times 3x over 3x times 4x over 4x times 4x over 4x. I'm just putting in enough factors of 3x and 4x that I'm going to be able to put the whole thing in this form and clear out all the 3x's and 4x's. So by rearranging this, I'm going to get, let's see, sine squared 3x over, I'm going to cross these out as I do them, I think. So I've used up that, and now I'm going to use up 2 factors of 3x. So let's use let's use 3x squared. Just use two factors of 3x. Now let's use two factors of 4x. Cross those out and put that over sine squared 4x. And then we have, of course, we have 3x, 3x, and 4x, 4x that we have to clear out. So that's going to be 3x squared and 4x squared. So there we go. And let's see what we can do here. So this comes out to the limit as x approaches 0 of sine 3x times sine 3x over 3x 3x times limit as x approaches 0 of 4x over sine squared 4x times 4x over sine squared 4x. All I did is I'm looking at this expression, I'm just sort of unwrapping it, so instead of writing sine squared, I'm just writing, oh sorry, I didn't do that right. This should be sine. Instead of writing sine squared, I'm just writing two factors of sine, and instead of writing 4x squared, I'm just writing two factors of 4x. We need, I guess, let's make this a little wider so I can do this. We need, sorry about that. We need one more factor of, we need to clear out the other factors rather. So this is going to be the limit as x approaches 0 of 3x squared over 4x squared. That takes care of this part. All right, so now we know is that this limit is equal to 1, 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 and this limit here, once we clear out the x squareds, that's just going to be, oh, sorry, there's typo there. Not really a typo, it's more of a righto. The squared should have gone on the outside. Once I clear out the x's, what I have left are 3 squared and 4 squared, so that's going to be 9 over 16. So the answer here is, in fact, 9 over 16. Now, some of you may observe that for certain types of limits, and I don't want you to do this because it doesn't work for every pair of trig functions, but you may have observed that I should have been able to read right off of here that I was squaring something with 3x and I was squaring something with 4x, and lo and behold, it comes out to 3 squared over 4 squared. It is in fact true that the limit as x approaches 0 of sine ax over bx is equal to a over b. So some of you are just going to say, well, wait a minute, why did you do that whole thing? Why can't I just do that? The answer is if that's what you're thinking, then you need to sort of get in the correct mindset for this course. This course is all about process. It's not a matter of just memorizing tricks like that. I mean, should you be able to use those to check your work? Absolutely. But should you be able to carry out the algebra that I just did to do the problem the full way? Yes, absolutely, that as well. And we of course have ways of checking this sort of thing, even on purely objective tests that you understand what the what the correct algebraic computation is here. So it's you really should understand what went on with the algebra in order to solve this problem rather than just memorizing a rule for the final answer. Like as I like to say, math doesn't. Many people think that if you can get the final answer, that's all it takes. But I say that math doesn't exist to be practical. Math exists to be beautiful. So if you just memorize a bunch of rules, you're ruining its beauty, and I get very sad.